In the previous video, we looked at how metals and nonmetals react with one another by exchanging valence electrons in order to form an ionic compound. We looked at how metals are more likely to lose valence electrons because they have a comparatively smaller number of valence electrons, and therefore it is easier for them to lose electrons in order to gain a full valence shell compared to nonmetals that tend to have a much larger number of valence electrons, and therefore for nonmetals it becomes easier to gain electrons from their metal counterpart in order to get a full octet of 8 electrons. Now in this video we want to look at how the reactivity of different metals compare to one another, as well as that of nonmetals, specifically by taking a look at the number of valence electrons that they have. Now, the easiest way to do this is actually to look at all of the metals within the same row, or rather within the same period of the periodic table. Now, what we're going to do on this side of the periodic table here is draw the dividing line, which is not actually a straight line, but is more of a staircase or a zigzag that segregates the metals that are found on the left-hand side of the periodic table from the nonmetals that are found on the right side of the periodic table. So if we take a look at these three metals here, sodium, magnesium, and aluminum, this version of the periodic table conveniently lists off the number of valence electrons that each element has. So sodium, as we can see, only has 1, as all alkali metals do. Magnesium has 2, as all alkaline earth metals do, and aluminum has 3, along with its counterpart metals in the same group, gallium and indium. Now, as we know, metals preferentially lose valence electrons because, once again, if we take a look at sodium, it's much easier for sodium to lose 1 valence electron than it is to gain 7. This is also true for magnesium. It's easier for it to lose 2 than it is to gain 6. And even for aluminum, that has 3 valence electrons, it's easier for aluminum to lose 3 than it is to gain 5. Now, in order to predict which metal is more reactive than the others, all that we need to do is consider which metal within the period is more likely to lose electrons than the other element. Now, sodium is the obvious case here, because if we see losing 1 electron is going to be much easier for sodium than losing 2 or than losing 3 in the case of aluminum. And from this, we can predict that of sodium, magnesium, and aluminum, sodium would be the most reactive. And so we can create an arrow here, and we can label this arrow as increasing reactivity. So what we can see is that metal reactivity increases leftward alongside the periodic table, specifically when we're referring to the metal side. So because sodium here has fewer valence electrons than magnesium or aluminum, we can say that sodium is more reactive than both of them, because losing 1 valence electron is easier than losing 2 in the case of magnesium, or definitely 3 in the case of aluminum. Now, in the second half of this video, we want to consider this same trend when we refer to nonmetals. And even though you might be tempted to follow the trend pattern of metals, this would actually be a mistake, because nonmetals, conversely, are more likely to gain electrons rather than lose. For example, with fluorine here, fluorine has 7 valence electrons, meaning that it only needs to gain 1 valence electron in order to have a full outer shell of 8. Oxygen, likewise, having 6 valence electrons, only needs to gain 2, which is significantly easier than losing 6. And even nitrogen here, that has 5 valence electrons, it is easier for nitrogen to gain 3 than it is to lose 5. Now, if we look at this simple pattern here, it's simply finding which element needs to gain the least number of electrons, or the fewest number of electrons, rather, we can see that fluorine, again, if we stick to the same period here, comparing nitrogen, oxygen, and fluorine directly, we can predict that fluorine is the most reactive out of all of them because it is easier for fluorine to gain 1 electron than it is for oxygen to gain 2 or for nitrogen to gain 3. And this is exactly what we see. So likewise, with the metal side of the periodic table, we can create an arrow here that indicates increasing reactivity for the non-metal side, only we can see that based on valence electrons, non-metal reactivity actually increases rightward along the periodic table, as this indicates which element needs to gain a smaller number of valence electrons than other nonmetals within its period. Now, there is actually one exception to this trend, and we can make a modification to the arrow and have it stop here shortly before the final family of elements on the rightmost side of the periodic table, which an inquisitive student will recognize are our noble gases. Now, the noble gases are special because if we look, especially with neon, argon, krypton, and xenon, we can see that all of these elements already have 8 electrons. And of course, helium being the exception, it only has 2, but the significance of this is actually the same, in that all noble gases, including helium, already have a full valence shell. So neon and below already have a full octet, and helium doesn't actually need an octet because we remember the first shell of electrons has a maximum of 2. So every single one of these elements in the noble gas family already have a full valence shell, and therefore noble gases don't need to lose electrons because then they would be giving up a full valence shell, nor do they need to gain electrons because that means they would be adding electrons on top of a full valence shell, which doesn't really make a lot of sense to do. And consequently, the noble gases are an exception to the increasing reactivity of nonmetals because noble gases already have a full valence shell and therefore are generally quite unreactive as far as nonmetals go. Before you move on to the next video, you can take a look at the practice problem below, which gives you 2 practice questions. In the first question, your job is simply to identify the elements on this list here and consider their Lewis structure in order to consider the number of valence electrons, and based on that, predict which of these metals would be the most reactive of them and give a basic explanation behind your justification, and then do the same with the nonmetals below. And in the final video in this series, we're going to take a look at how metal and nonmetal reactivity changes vertically on the periodic table, which will require us to put our knowledge of atomic structure to use.